Okay, so today we're finally going to do the general Cauchy theorem, right? So that's the plan for today. We might even do a bit more than this. We'll see. And I mean, by now we have already obtained most of the applications of Cauchy's theorem, at least to understand regularity of analytic functions. But what we're going to do today is actually understand when is it that Cauchy's theorem is true, right? So for which curves and which domains is Cauchy's theorem true? And this will actually tell us quite a bit about the domains and the curves, right? And so in a way, you can view what we're going to do today as sort of the starting point of algebraic topology, right? Where it's not clear at all where the algebraic side of is yet. It's clear that there's some topology going on, right? So let me write just general, general or more general Cauchy's theorem, right? So that's what we're going to do today. Right, and so the question we really want to understand today is for which, right? So for which regions omega and curves and the closed curves. Let me maybe write. And for which closed curves gamma is Cauchy's theorem true? Right, so this is the question that we want to answer today. Right, so to understand regularity of complex functions and very local properties, right, we don't actually need this, so to say, right? Because our strategy so far has been that we know Cauchy's theorem is true for a disk, right? And so every time we want to study local properties, we just zoom in around, right? If there's some z and omega, whatever omega looks like, we just zoom in a disk. Wait. The disk shouldn't intersect the boundary, right? We just zoom in a disk around z. Cauchy's theorem is true for that disk, and then we just do everything on that disk, right? So in a way, Cauchy's theorem for a disk already allowed us to do everything for local properties and regularity of analytic functions. But now this is a very general, very natural question, right? Okay, but when is it actually true, right? And it's not, I guess, first observation is not always true. Right, it's clearly not always true, right? Because, if I take omega to be, say the unit, say the complex numbers, taking away 0, right? And then I take omega just to be, say, the circle centered at 0 and with radius 1, right? Centered at 0 and radius 1. We know that the integral of 1 over z dz is not 0 on the circle, right? In particular, it is 2 pi I times the winding number, right? So even though, of course, 1 over z, right, fz equals 1 over z is analytic in omega, right? So this theorem is not always true, clearly, and we want to understand exactly when it's true. And in a way, before I get into the actual theorem, in a way, this is sort of the only case in which it's not true, so to say, right? So the issue with this set omega is that there is a point at 0 that doesn't belong in omega, and then you have, say, we can think of let's think instead of being all of c. Maybe it's just c up to a certain, certain ball. Let's imagine that it's bounded it'll be easier to draw a picture. Right, so the problem is exactly that there's a point in the middle that is not part, right? So there's this point here. And so omega has this property that is sort of holes in it, right? And the problem is exactly that this curve, gamma, is going around the hole. Right, is exactly the problem that if I loop, if the curve gamma loops around the hole, right, this seems to be exactly the problem, right? And the winding number is an integral of a function that's analytic everywhere except the place where we're winding around, right? And so the intuition is that this is sort of the only problem that can arise. And as long as every curve gamma, right, doesn't wind around anything that's not on omega, then Cauchy's theorem should be true. Right? So before we prove it, let me again say sort of the intuition. The right way to think about this is as long as gamma doesn't go around something that's not in omega, then Cauchy's theorem should be true. And in particular, if we can grab gamma and we can sort of contract it all the way to one point, right? So if omega, instead of being that curve, was this one, say, right, then it would be okay, right? There's nothing bad in the middle. We could just pick omega and continuously contract it to nothing. And this would be, and then the integrals around it would be 0, right? So this is the intuition, right? And so sort of it's important to give the definition of simply connected, right? Right. So simply connected will be exactly a set. So simply connected, this will be an important property, and basically means omega has no holes. Okay, this is of course not a definition, so right, but this is the intuition, right? And now let me give an actual definition. Okay. So maybe I'll draw another picture, right? So this one here is simply connected, while say this, right, with this inside not in the right, so omega being just this part without the inside is not simply connected, right? Because it has a hole in the middle. Okay, so how do we define this? There's a few different ways of defining it. Now, I should make, for those interested in topology and learning more about algebraic topology and so on, I should start by making a disclaimer that what I'm going to do now, I'm going to sort of avoid a lot of the difficulties that arise in algebraic topology and all this, by giving definitions that work very well for 2 dimensions and the complex numbers, but they're sort of not the right definitions for higher dimensions. I will still talk a little bit about what would be the right definitions, but this will make everything a lot cleaner and will make proving Cauchy's theorem a lot easier. Okay. So let's give definition. Okay, and important to note that this is the right definition of simply connected for regions of the complex plane, right? Not for if you want to study higher dimension topology of say varieties or something, right? So definition, right? A region, right, is simply connected, right? If and only if, right? The extended plane, say C. Let's call C with infinity here, right? So this is the extended plane. So the plane with infinity, right? If and only if C infinity without omega is connected. Okay, so in this case, right? In this case, everything that's not in omega is just everything outside of omega is definitely connected. While in this one, right, in this one, it's not, right? There is, there are 2 parts. The complement of omega has this part here and has this part here, and they're not connected, and so this set is not simply connected. Okay. Okay, and in particular, right, we can now draw a bunch of examples. Right, examples say a half space. Right, the half space is simply connected, a disk, right? So things that are simply connected, right? Things like a half space, a disk, say a band, right? So all z such that, say, the real part of z smaller than 1 and smaller than 0 and bigger than 0, right? Yes, very good. So someone asked, why is it important that I take the extended plane? Right, here's one place where you can see that. Right, so the band, if I take let me see if I have chalk. Right, if I take complex numbers and I take this band, right, then this is simply connected, and even though in C the parts on they are not connected, right? So taking the the extended plane is important. And it'll be important in some of the things that we're going to say. Okay, so things that are not simply connected. Right, but the region omega is in C, not in C infinity. So the infinity point always belongs in the complement of C. Okay, things that are not simply connected, say an annulus. Right, so if I have, say, this set omega, this is not simply connected, right? Because the complement of omega has this part and this part, right? A punctured, let's say, C without a point A, right? And again, this is a place where taking the extended plane is important, right? Because now the complement of this region is A and the point at infinity, and it's not connected. So this set is not simply connected. Okay. Okay. So just as as an observation, if you want to work in high dimensions, the right definition for simply connected is that every curve in the region, okay, so I'll just give this very intuitively, right? So basically, a set is simply connected if every curve, gamma, closed curve around the region, can be contracted to a point, right? So, you can imagine doing some kind of continuous operation on this closed curve and contracting it to another curve and so on. And if you can contract the curve all the way to a point, and if you can do this for every single curve, then the set is simply connected. Okay? And this is sort of the right definition for higher dimensions. And if it's worth just thinking about, if you have a curve in this set, you can definitely contract it to a point. Same thing as a disk, same thing as in a half space, and so on, right? While in the annulus, you definitely cannot, right? Because in the annulus, if I have a curve that loops around, the hole in the annulus, I cannot contract it to a point. And same thing for C without A, right? If I have a point A, and I have now a curve that goes around A, I cannot contract it to a point, right? A is not a point in the set, so it's not a point I can contract it to. If I try to contract it somewhere else, right, I get stuck on A, right? I can't go past A. Okay? And so really a set is simply connected if every curve can be contracted to 0. Now, for taking this approach of contracting and so on, forces to talk about continuously moving the curves and all this stuff. And the very nice thing is for complex analysis, we actually don't have to get into any of that. And this definition is going to be plenty enough. Okay, and so now, but still, let me give a sort of an equivalent definition, still in the complex plane, that is, that is more, that will be more useful even than this one, and I'll prove that it's equivalent to this one. Okay, just as an observation before we go, just to argue, before we go to the next thing, just to argue, why this is sort of maybe not the right definition for higher dimensions, is if you take, although for higher dimensions, I wouldn't be looking at things like Cauchy's theorem and so on, but it's still interesting to look at topological properties of your space, right? If I take, let me see if I can draw this. If I take a sphere, right, and I take, say, a core from inside of it, think of like the crust of Earth or something, right? So, think of a big sphere with another sphere, with a little sphere removed on the inside, right? Like a chocolate egg with the thing removed on the inside, right? The complement of this is definitely not connected. However, it's not so hard to see that any curve that I draw, right, any curve that I have around, I can always contract it to a point, right? Because I can avoid the inner part by just making the curve go up first, say, right, and then close it. Okay. And so that, right, okay. So this is just one example to have in mind, but from now on, we're just going to be in the complex plane. And so this definition is an excellent definition that doesn't need us to get into any, like annoying things with having to worry about what it means to continuously move something and so on and so forth. Okay, so let's give an equivalent formulation of this definition, which will be much more in line with, with the intuition I was giving. Okay, so theorem or proposition. Let's take again a region, right? Is simply connected if and only if for all omega closed curve in omega, right? Any gamma closed curve in omega, and any a not in omega, we have that the curve does not wind around a. Right? This feels like a lot better of a definition, right? And it's this idea that, any point outside of any curve, so let me again draw, right, omega, right? Any curve inside omega, doesn't matter what it does, I should make it look continuous, right? Any curve omega, and any point a, gamma, and any point a outside of omega, gamma never loops around a. Right, so such a set would be simply connected, while again, a set that is not simply connected, okay, take away this part, then I can definitely just pick a in this part here, and curve gamma inside my set omega, and it will definitely loop around a. Right, so and a is not 0. In this case, is 1, while here it is 0. Okay. Okay, so let's prove this proposition. Okay, just to start doing some topology. Okay, so there's two parts to this proof. One is easy and another one is a little bit trickier. So let's do this, because then the proof of Cauchy's theorem is actually quite similar to this one. Okay, so proof. Okay, so let me make sure which one is which. So simply connected, then any closed curve. Okay, so let's do this one. So this is the easy one. Okay, so let's take right, the region, and let's take gamma, okay, in my curve. Right, okay. And now let's take, right, let this be the interior of the curve, be the inside of the curve. Okay. Okay, it's a lot easier. So since the complement of omega in C infinity is connected, right? Since this is connected, it must be inside one of the regions made by gamma, right? It must be inside one of the regions delimited by gamma, right? Because gamma does not intersect because gamma does not intersect omega, right? So let me erase this part now. Okay. Now, so omega complement needs to be in one of the regions delimited by the curve gamma, right? Since the point at infinity is inside the complement of omega, we must have, right? It must be that the complement of omega is contained in the region, in the unbounded region. Determined by gamma, right? So in particular, it means that, it's the same thing as saying that now it needs to be in the unbounded region, so the inside of the curve does not, is not in omega complement. And so in particular, this means that for all A in the complement of omega, A is not in the curve or the inside of the curve, and so the winding number needs to be 0. Okay, because so a connected set needs to be in one of the regions delimited by the curve. Otherwise, I could split the connected set and it wouldn't be connected to start with. And because it contains the point at infinity, it needs to be in the unbounded region. And in the unbounded region, we prove that the winding number was 0. Okay, yeah, I had sorry, I hadn't seen the questions. Yeah, I set it up this wrong in the beginning, but now it's fine. Yeah, let's say yeah. I mean, not wrong. It was just not the right way to set up to prove this easily. So what is, again, the definition? Region is a set open and connected, right? Region was, in this course, is open and connected. Wait, do I have a C missing somewhere? So let's say, yes, here, sorry, okay. It's good, thanks. Is there any other typo? Okay, let me go over this since, okay. So I have a region, a curve inside the region, okay, and let's say the interior of the inside of the curve. Since the complement of the region is connected, it must be inside one of the regions delimited by gamma, right? It could be, there's, in this case, there's only 2, right? There could be more, of course, if gamma loops around and hits itself a few times. Okay, but it must be inside one of these regions. Right? And because the point at infinity is in omega c, it must be in the unbounded region. And so because of that, right, if it's in the unbounded region, we know that any point in the unbounded region that's determined by a curve has winding number 0. Here, okay, unbounded. Okay, maybe I'll write it here instead. Okay, Okay, so let's now go to the difficult part of the proof. Okay, this was easy, but not set up the right way, it's still not trivial. Okay, all right, so let's go to the easy part of this. The difficult part. So let me erase this. Because this one, I mean, it's not that it's more difficult, it's just that you have to work a little harder. Okay. Okay, so now this part, which is a bit harder. Okay, so let's set up this construction. Okay, so let's see how much time I have. Yeah, okay. So now, here is determined, yeah. Okay, sorry, I'll try to be better with my handwriting. So I'm using the words determined and delimited in interchangeably. Okay. Okay, so this is the harder part. So let's say that, you know, the complement of C in the complex in C infinity is not connected. Okay, so we know that, you know, the complement is closed, right? So let A and B be two closed sets such that A union B is equal to the complement and they don't intersect. Right? Because the complement is disconnected, then this must be true, right? Such a thing must exist. Okay. Now, one of them needs to contain infinity, the other doesn't, right? So let's say that A is bounded, right? And so if one of them contains infinity, the other one needs to be bounded. So let's say let A be the bounded one. Okay, so now let me draw a picture to help. So I'm going to draw omega. Okay, let's see if I can draw a good picture. And now I have A. So, right, omega is something like this, in which the complement is not connected. And I'm taking A to be this set and B to be this one. Okay? Now, of course, you know, omega could have many holes, and then those other holes could belong to either A or B. Right? The important thing is that B is the n-bounded part, and A is the bounded one. Okay, so now what's going to be the strategy? Right? I mean, the strategy will be to show, okay, before we actually go with the proof, the strategy will be to try to make a curve go around A and argue that this curve towards a point A in A has winding number that's not zero, right? Sort of the proof by picture sort of done already, right? Because if I have a picture like this, I mean, of course, the proof by picture is not really a proof by picture because I haven't convinced you that omega looks like this, but right, I'm going to set a point A in A, and I'm going to try to construct a curve that goes around A, and therefore has winding number positive with respect to the point A, without ever intersecting B, right? And so while being inside omega. Okay, so let's do that. So let's say, let delta be the distance between A and B. Between A and B. Right? For sure, because the sets are closed, omega is bigger than 0. Right? They need to have a distance bigger than 0. Okay, so this So this what will allow me to do is will allow me to now try to build a curve, right? Because I know that I have a slack of at least delta bigger than 0. And so if I draw, for example, a curve that stays always less than delta over 2, say close to the set A, then I make sure it doesn't intersect B, right? That's exactly the strategy. And in particular, we're going to fill the omega with a net of squares, right? So fill with a net of squares. So let me do a picture. Okay, so let me see if I can draw a good picture, right? So take something like this. And so on and so forth. Okay, so I'm drawing a net of squares around all my set omega, right? So it goes on. Okay, and now clearly I want to do this to make sure that if a square contains a bit of A, it doesn't contain a bit of B, right? So I'm going to do it in a way to make sure that when I take my square, that the diagonal in the square is smaller or equal than delta. Because if I do that, I make sure that I never get in the same square something from A or B. So the net of squares with side length right, with side length smaller or equal than 1 over root 2, smaller, say, 1 over root 2 delta, right? Because if the side length is smaller than that, then I can never, right? Then this is smaller than delta, and so I can never touch both sets with with just one square. Okay. Okay. So far, so good. There was another question. So I think this is from a typo from before. This question. So it's omega gamma intersected with omega complement is empty, not omega. There was a complement missing here earlier. I think that's what the question that's on the chat is about. If anything else, please, let me know. Might have missed somewhere. No, I think so far so good. Okay. So now I'm going to create, right? So now what is a natural way of creating the curve? I'm just going to create the curve that goes around, right, the sides around A. And this curve will for sure not touch B, right? So how do I create this, right? I say, I take Qj for J in some set J, the squares that intersect right, that intersect A. Okay, so Qj's such that, and let's say that the squares are the interiors, intersected with A is an empty. Okay, so they intersect A, right? And so I'm taking these squares. Okay, so this is what my index J is. Okay, and now what's going to be my curve is going to be the boundary of this set, right? So I can just take the sum of the curves of the boundaries of each one of these squares, right? Because if I take the boundary of each one of these squares, I get, right, these ones cancel out, and I get exactly the boundary of this set. Okay, so let's do that. Let me erase that part. Was there anything else that's not? I see something in the chat. Let's see. Sorry. Okay. No, it's okay. There is a complement here. Yeah, okay. Right? It's all good, or is there any? Okay, if there's any issue. Okay, great. Thanks. Yeah, thanks for pointing out this. I mean, it's very easy to miss a complement somewhere. And so I try to draw the picture so that we're all on the same page of what's going on. Okay, so let me... Right, in this proof, there is one idea, and it's the picture. And then you have to, do the math to check that the idea works. But the idea is that picture, basically. Okay. Okay, so now let's take the curve gamma to be equal, right, to the sum for each little j in this set j, right? So basically where qj intersects A, right? And we take the boundary of qj. Right? And so because of the construction, right, the boundary doesn't intersect B, right? Because of the cancellations, so the boundary, so clearly, this curve gamma does not intersect B, right? Because the distance between A and B was bigger or equal than delta, right? So maybe I'll write it here. It's bigger or equal than delta, right? So since they intersect A, they cannot possibly go all the way and intersect B because the diameter of the square is smaller than delta. Also, they don't intersect A because of the cancellations, right? Because if a point, if a point in the boundary of the square is inside of A, right, then it would be canceled out because it would show up in two of the squares, one pointing in one way and another pointing in another, right? So because of cancellations. Okay. It is also clear, right, that n, so this means in particular that gamma, right, needs to be inside omega, right, because it's not inside B or A. Okay. And also, right, clearly n, right, we can do this whole construction. We just have to make sure, say, we can do this whole construction such that A is in the center of one of the squares, right? We just have to make sure that it's not in the boundary, right? So we can get a net of squares, and we can make A be in the center of one of these squares, right? Or be, so, right? We can easily ask for A to be in the center of one of these squares, and so for sure, this is equal to, right, the sum of these of the winding numbers of all those curves, but the winding numbers of these curves of the squares that are outside that don't touch A are for sure 0, and so the only one that we get is the one that intersects A, right? So this is the winding number, right, of the Q, say, let me call A, right, A, right, where QA is the square with A inside, right? And this is 1, which is not 0, right? And so we constructed a curve whose winding number on a point, right? So, right, A is in our set A, so it is in omega complement. And because of our construction, the winding number of that curve around the point A is not 0, it is 1, and this proves what we want, right? We wanted to show that if it's not simply connected, then the winding number wasn't 0, okay? And here I can just say, right, I can pick with A in the center of one of them, Okay, and here by by Qj I mean like the open square, or you can ask that the interior doesn't intersect A. Okay, so this proves our proposition, right? So one side was very simple in the sense that it didn't need any idea, right? And now we just this one requires an idea, requires to construct a curve, but we can explicitly construct a curve. Okay, I see there's some questions. Okay, so there was a question. Okay, this is because of what's open and what's closed. So there was a question. It was a very good question of why are we sure that the curve? Wait, which curve? The curve? You mean the curve that we just constructed? Okay. Okay, so what's the problem? Let me think. Okay, yeah, this shouldn't be open. This should be the closed. This should be the closed square. You're right. Okay, right. So this is a net of squares, and Q of j is the closed square. Okay, so that when I right, so that if so let's see what happens at the boundary. Okay, let me see if I can make another picture. Maybe up there. Right, so if I have, let's say I have A, and now I have a square that hits right here, right? This is the problem that could arise. Then the square to the right gets counted as well, right? So the square to the right, this one also, let's say Q, this Q intersection with A is also an empty. Right, and so the way that this is constructed, if a point is in the boundary of one of the QJs, it will be in the boundary of two of the QJs, and so we will cancel out in the curve, and so we will never show up in the curve gamma. Yeah, I had written here earlier open, but right, it's definitely closed. Yeah, so I mean, maybe I should be a bit more clear here. If a point B is in A and in a QJ, then it is also in another QJ prime, right? And so it cancels out. Okay, I'll make sure that this is all okay. Yeah, I mean, the only thing we need to be careful is not to draw the squares with A in the boundary of the squares. But we can do, right, we can just fix a point A, then fix a net where A is in the center of one of them, and then this problem doesn't arise anymore. Okay, any other questions? If not, then we'll be back in 10 minutes to the actual proof of Cauchy's theorem.